Look up at the night sky, and you'll see countless stars, planets, and moons, each one a world of its own, shaped by forces we're only beginning to understand. But what if I told you there's something out there far stranger, something that defies logic, scattered across the cosmos, hidden among the darkness, are moons that shouldn't exist? Not because they're impossible, but because they're identical. Picture this: two moons orbiting stars light years apart, yet their surfaces bear the same scars, the same cracks, the same hauntingly familiar patterns, as if someone copied and pasted them across the universe. This isn't science fiction, it's real. Scientists have catalogued at least 25 of these mysterious moons, celestial twins separated by unimaginable distances, and their existence challenges everything we thought we knew about how planets and moons form. How can two worlds, born in different corners of the galaxy, end up looking like mirror images of each other? Is it a cosmic coincidence, or could there be forces at work we haven't even discovered yet? Some researchers point to ancient collisions, violent events that might have sculpted these moons in eerily similar ways. Others whisper about exotic materials or even unknown laws of physics that could be shaping these distant landscapes in unison. And then there are the myths, stories from cultures across Earth that speak of mirrored heavens, of celestial doubles watching over us. Could our ancestors have glimpsed something modern science is only now uncovering? This is more than just a puzzle for astronomers. It's a window into the deepest mysteries of the universe. If these moons are connected in ways we can't yet explain, what else might be hiding in the shadows of space? Over the course of this video, we'll journey from the earliest observations of these enigmatic worlds to the cutting-edge theories trying to unravel their secrets. We'll meet the scientists racing to solve this cosmic riddle, explore the mind-bending possibilities, and maybe, just maybe, catch a glimpse of how much we still have left to learn. So buckle up, the universe is about to get a whole lot stranger. Among these strange celestial doppelgangers, two stand out as the most tantalizing: Europa and Enceladus. One dances around Jupiter, the other around Saturn, separated by hundreds of millions of miles, yet their surfaces could almost be mistaken for the same world. Both are frozen spheres, their icy crusts cracked like broken glass, with vast networks of fractures crisscrossing their landscapes in near-perfect symmetry. But the real mystery lies beneath that ice. Plumes of water vapor shoot into space from both moons, betraying the presence of hidden oceans, liquid water trapped between layers of rock and ice. Think about that for a moment. These aren't just dead, frozen rocks. They're active, dynamic worlds with forces beneath their surfaces shaping them in ways we're still struggling to understand. The parallel fractures on their faces. Scientists believe they're the work of tidal forces, the relentless gravitational tug of war between their massive parent planets and neighboring moons, stretching and squeezing these icy shells until they crack in eerily similar patterns. It's as if Jupiter and Saturn, two vastly different giants, somehow sculpted their moons with the same invisible hands, but the similarities don't stop there. Both Europa and Enceladus show signs of hydrothermal activity, hot vents on their ocean floors, much like those in Earth's deepest seas where life thrives without sunlight. That's why astrobiologists can't stop staring at these icy twins. If life exists beyond Earth, these might be the places we find it. The same forces that carved their surfaces could also be fueling the chemistry needed for life deep below. So are these moons cosmic siblings, shaped by the same universal processes? Or is something even stranger at work? The more we study them, the more the lines blur between coincidence and something deeper. Europa and Enceladus aren't just mirror images, they're windows into the hidden forces that shape worlds, and maybe, just maybe, the cradle of life itself. While Europa and Enceladus dazzle with their icy symmetry, another pair of cosmic twins takes the mystery even deeper, into the realm of alien atmospheres and liquid landscapes. Meet Titan and Triton, two moons separated by billions of miles, yet bound by an uncanny kinship. Titan, Saturn's golden giant, and Triton, Neptune's captured wanderer, shouldn't have much in common. One basks in the faint glow of a distant sun, the other drifts in the frozen outskirts of our solar system, but peer beneath their hazy veils, and the parallels are impossible to ignore. Both are shrouded in thick nitrogen atmospheres, rare among moons, and both dance with methane, a molecule that behaves here like water does on Earth, falling as rain, pooling in lakes, even carving riverbeds into their exotic surfaces. Imagine a world where the air itself is thick enough to swim through, where icy dunes stretch for miles, sculpted by winds we can barely fathom. Titan's dunes, made of organic sand, ripple across its equator like the deserts of Namibia, except here the sand might be frozen bits of hydrocarbon snow. Triton, meanwhile, boasts its own surreal landscapes, cantaloupe terrain, a cracked, bumpy surface unlike anything else in the solar system, alongside geysers spewing nitrogen gas miles into its thin sky. Yet despite their differences, both moons share something profound: active weather systems. Titan's methane storms might not be so different from Triton's nitrogen plumes. Both hint at cycles of evaporation and condensation, just with ingredients stranger than anything on Earth. What's truly baffling is how these processes could arise in such distant, hostile environments. Titan orbits relatively close to the Sun, such as it is out there, while Triton spirals in the frigid dark, a captured Kuiper belt object that shouldn't have retained such dynamic features. Some scientists argue tidal forces again play a role, flexing these moons' interiors to keep them geologically active. Others speculate about subsurface reservoirs, hidden oceans of ammonia or water, perhaps churning beneath the ice and driving surface changes. But the most tantalizing theory, that these moons are following a universal recipe, one where nitrogen and methane, under the right conditions, inevitably create worlds with dunes, lakes, and storms. If that's true, it rewrites the rules of planetary science. We've long assumed that Earth-like conditions were rare, that liquid on a moon's surface was an anomaly. But Titan and Triton suggest something else entirely, that given the right ingredients, nature might paint the same landscapes across the cosmos, no matter how far apart the canvas. And if that's happening here in our own solar system, what other mirrored worlds might be waiting among the stars? The nitrogen duo doesn't just challenge our understanding of moons, it hints at a galaxy where the familiar and the alien might not be so different after all. If you thought Europa and Enceladus were strange, or Titan and Triton defied expectations, wait until you meet Io, Jupiter's fiery rebel. This moon doesn't just have volcanoes, it's the most volcanically active world in our entire solar system. A place where lava lakes bubble like cauldrons and eruptions paint the sky with plumes taller than Mount Everest. But here's where it gets eerie. Across the cosmos, astronomers have spotted an Examoon, a moon orbiting a planet outside our solar system, with a volcanic region called Loki Patera that looks like someone took a snapshot of Io and pasted it light years away. The resemblance isn't just superficial. Both feature vast, hellish lava lakes with shorelines that shift and crack. Both spew sulfur-rich magma in clockwork like eruptions, and both glow with the same unearthly heat. How can two moons born around different stars mirror each other so precisely? The answer might lie in the hidden forces that drive their infernos. Io's violence comes from tidal heating, a gravitational tug of war between Jupiter and its neighboring moons that stretches and squeezes Io's interior like putty, generating enough friction to melt rock. But Patera's host planet isn't a gas giant like Jupiter. It's a different beast entirely. Yet somehow, the same processes seem to be at work. Scientists suspect that certain moon-planet relationships, no matter where they form in the universe, might inevitably create these sulfurous pressure cookers. It's as if the cosmos has a recipe for volcanic moons, and once the ingredients align, a massive planet, a close orbit, and a moon with the right composition, the result is always the same: a world on fire. The implications are staggering. If volcanic moons obey universal rules, then Patera might just be the first of many we'll discover. Imagine entire galaxies dotted with these molten twins, each one a testament to the predictable chaos of cosmic chemistry. And that raises another tantalizing question. If volcanoes shape moons so predictably, what else might follow the same cosmic blueprint? Could there be other mirrored features, craters, mountains, even underground oceans waiting to be found on distant worlds? Io and Patera aren't just curiosities. They're clues, hinting that the universe might be far more repetitive and far more knowable than we ever dared to dream. Jupiter's largest moons, Ganymede and Callisto, present another cosmic riddle, one etched in craters and frozen in time. At first glance, they couldn't be more different. Ganymede, the solar system's biggest moon, boasts a magnetic field and a hidden ocean beneath its icy shell, making it a dynamic, evolving world. Callisto, on the other hand, is a battered relic, its surface so ancient it's practically a fossil record of the early solar system. Yet when you zoom in, their scars tell the same story. Both are pockmarked with eerily similar craters, their surfaces bearing the same shadowed imprints, as if struck by the same celestial hammer. How could two moons with such different fates share these identical wounds? The answer might lie in a forgotten chapter of our solar system's history, a time of chaos known as the Late Heavy Bombardment. Picture this: billions of years ago, the outer planets shifted orbits, hurling asteroids and comets into a deadly pinball game across the solar system. Ganymede and Callisto, sitting in Jupiter's gravitational crossfire, would have been prime targets. But here's the twist: Ganymede's grooves, those long, sweeping trenches carved into its ice, suggest it was geologically active long after the bombardment ended, its surface constantly renewing. Callisto, frozen in time, should have preserved a completely different record. Yet their crater patterns align almost perfectly. This paradox has scientists scrambling. Some propose that Jupiter's gravity funneled debris into a shared storm of impacts, striking both moons in synchronized barrages. Others wonder if Ganymede's grooves aren't just scars from impacts, but tidal cracks from an ancient dance with Jupiter. Cracks that later filled with icy lava, preserving the bombardment's marks in a way that mimics Callisto's untouched surface. Either way, these cratered cousins are more than just neighbors. They're time capsules holding clues to a violent era that shaped not just Jupiter's moons, but every world in our cosmic backyard. And if Ganymede and Callisto were shaped by the same forces, what does that mean for other moons in distant star systems? Could crater patterns be universal fingerprints, left by chaotic beginnings we've yet to uncover? The more we study these mirrored surfaces, the more we realize the solar system's history isn't written in stone. It's written in ice. Saturn's moons Mimas and Tethys look like they've stepped straight out of a science fiction epic, and not by accident. Mimas, with its gaping Herschel crater stretching nearly a third of the moon's diameter, is often called the Death Star moon, for its uncanny resemblance to the iconic Star Wars battle station. But here's the twist: Tethys, another of Saturn's icy satellites, sports its own colossal scar Odysseus crater, a sprawling impact basin so large it could swallow entire cities whole. Both craters are eerily similar in shape, with steep walls and central peaks, as if sculpted by the same cosmic catastrophe. What are the odds that two moons orbiting the same planet would bear such strikingly identical wounds? At first glance, it might seem like random chance, a fluke of celestial violence. But when you dig deeper, the numbers don't add up. Craters this massive are rare, the result of impacts so violent they should have shattered these moons entirely. Yet both Mimas and Tethys survived, their craters frozen in time like cosmic bullseyes. Some researchers argue this isn't coincidence at all. It's evidence of a shared trauma. Billions of years ago, Saturn's system may have been rocked by a swarm of debris, perhaps the shattered remains of a rogue moon or a passing asteroid torn apart by the planet's gravity. The same storm of fragments could have pummeled both worlds, leaving behind these mirror image scars. But there's another, even wilder possibility. What if these craters aren't just random hits, but the result of something far more precise? Computer simulations show that under the right conditions, massive impacts can create shockwaves that travel through a moon's interior, focusing energy on the exact opposite side, like a cosmic echo. If a second impact struck that antipodal point, it could explain why both Mimas and Tethys ended up with such perfectly centered craters. It's as if the universe itself lined up the shots, ensuring these moons would wear their scars like matching badges. And if that's true, what does it mean for other star systems? Astronomers have already spotted exomoons with similar colossal craters worlds light years away that seem to mirror Saturn's battered satellites. Could there be a universal rulebook for how giant impacts shape moons, no matter where they form? Mimas and Tethys aren't just curiosities. They're testaments to the violence lurking in even the most serene corners of space. And if these icy sentinels are any indication, the cosmos might have a dark sense of humor, crafting doomsday craters so perfect they look almost intentional. Uranus holds some of the strangest moons in our solar system, but none are quite as puzzling as Miranda and Ariel. These frozen worlds look like they've been shattered and hastily glued back together by some cosmic hand. Their surfaces a chaotic patchwork of cliffs, canyons, and plains that don't seem to belong on the same body. Miranda, in particular, is a jumbled masterpiece, its terrain so fractured that one region, Verona Rupes, boasts cliffs over 12 miles high, making them the tallest known in the solar system. Ariel, meanwhile, is crisscrossed with vast networks of grooves and ridges, as if its crust was pulled apart and stitched back together in a hurry. What could have caused such bizarre, matching destruction? The leading theory points to tidal forces, Uranus' lopsided gravity stretching and squeezing these moons over eons, heating their interiors until their icy shells cracked like eggshells. But there's a problem. Uranus' tide shouldn't be strong enough to wreak this much havoc. Unlike Jupiter or Saturn, Uranus doesn't have massive neighboring moons to amplify the tug of war. Some scientists speculate these moons might have been victims of a cataclysmic past, perhaps a collision that shattered them entirely, only for their fragments to slowly reassemble under their own gravity, leaving behind these scrambled landscapes. Others suggest cryovolcanism, where underground oceans of slushy ice erupted to the surface, warping the crust into these jagged puzzles, the eeriest part. Miranda and Ariel aren't just randomly fractured, their scars follow similar patterns. The canyons on Ariel mirror the grooves on Miranda, as if both moons were subjected to the same violent stress test. This raises a haunting possibility. that Uranus' entire moon system might have endured a shared trauma, some ancient event that left its mark on multiple worlds at once. Could a rogue planetesimal have plowed through the system, scattering debris that later rained down as a storm of impacts? Or did Uranus itself, tipped sideways by a colossal impact, trigger tidal quakes that rippled through its moons in unison? These jigsaw moons don't just challenge our understanding of geology, they force us to rethink how moons evolve in isolation. Most moons show signs of steady, predictable change, but Miranda and Ariel seem to have lived through moments of violent reinvention. And if that's possible here, in the quiet outskirts of our solar system, what other shattered worlds might be waiting in the darkness? Their fractured faces aren't just scars, they're pages from a history book we're only beginning to decipher. Pluto's moon Charon might be small, but it holds a big secret one that stretches across the cosmos. Its surface is streaked with dark, rust-colored patches, a stark contrast to the bright ice surrounding them. These strange stains come from Tholons, complex organic molecules formed when methane and nitrogen are zapped by radiation, creating a sticky, reddish gunk that paints the landscape. But here's the twist: light years away, an Examoon named Hydra orbits a distant dwarf planet, and its surface bears the same eerie stains. The resemblance isn't just superficial. Both moons are frozen, airless worlds, bombarded by cosmic rays and ultraviolet light, their surfaces slowly cooked into the same cosmic graffiti. What does this mean? Tholons aren't unique to our solar system. They're a universal byproduct of chemistry in the cold, dark reaches of space. Wherever you find methane and nitrogen exposed to radiation, Tholons seem to follow, like a shadow that clings to certain moons no matter how far apart they are. Scientists call this Tholon weathering, and it might be one of the cosmos' most reliable artists, splashing the same murky palette across worlds that have never met. But the real mystery lies deeper. These molecules aren't just stains, they're the building blocks of life's precursors. On Earth, similar compounds may have rained down in comets, seeding our planet with the raw materials for biology. So if Charon and Hydra are both coated in this organic sludge, could other moons, ones with warmer, hidden oceans, be brewing something even more complex beneath their Tholon-stained shells? The implications are staggering. We've long assumed that life's ingredients were rare, scattered unevenly across the universe. But if Tholons form this easily, on moons as different as Charon and Hydra, then the universe might be dripping with the stuff, a cosmic varnish that could be painting countless worlds in the same primordial soup. And that raises a tantalizing question. If Tholons are this widespread, how many other moons, lost in the darkness, are silently assembling the pieces of life right now? Charon and Hydra aren't just curiosities, they're clues, hinting that the universe might be far more generous with life's raw materials than we ever imagined. Saturn's moons Rhea and Dione might seem like quiet, frozen worlds at first glance until you catch the sunlight glinting off their surfaces, revealing something extraordinary. Streaks of brilliant white lace across their terrains like delicate brushstrokes on a cosmic canvas, tracing patterns so similar they could be siblings. These aren't random scratches, they're fractures in the ice, vast networks of cracks that stretch for hundreds of miles, glowing against the darker terrain like veins of lightning frozen in time. What could create such precise, parallel scars on two separate moons? The answer lies beneath their icy shells. Both Rhea and Dione are thought to harbor subsurface oceans, hidden layers of liquid water trapped between rock and ice, kept warm by the relentless tug of Saturn's gravity. As the planet's tidal forces squeeze and stretch these moons, their crusts fracture like thin ice on a pond, creating these luminous streaks. But here's the mystery: the patterns are almost too similar. On both moons, the fractures cluster along equatorial regions, branching in feathery, near-identical networks. Some scientists call them wispy terrain, a poetic name for a phenomenon that might hold the key to understanding how icy moons evolve. The eerie symmetry goes deeper. Close-up images from spacecraft reveal that these fractures aren't just surface deep, they're likely windows into the moon's internal histories. Some streaks appear younger, their bright ice unblemished by the dark dust that coats older regions, suggesting these moons have been cracking open and refreezing for eons. It's as if Rhea and Dione are locked in the same geological rhythm, their surfaces breathing in sync with Saturn's gravitational pull. Could this be a universal signature of ocean-bearing moons? Elsewhere in the solar system, Europa's icy crust is laced with similar fractures, though stained reddish by minerals. Even distant exomoons might sport these luminous scars, betraying the presence of hidden seas beneath their surfaces. If so, these wispy streaks aren't just curiosities, they're cosmic road signs, pointing us toward worlds where life could be stirring in the dark. And that raises a thrilling possibility. If we learn to read these icy hieroglyphs, we might just unlock the galaxy's best-kept secrets. Uranus keeps its secrets well hidden, but two of its largest moons, Oberon and Titania, might be the key to unlocking them. These frost-covered giants, though distant from each other in orbit, wear nearly identical coats of ancient ice, thick, glittering layers that have preserved their surfaces like time capsules from the solar system's violent youth. Peer at their images side by side, and you'll struggle to tell them apart. Both are pockmarked with craters, their plains dusted with the same pale frost, as if sculpted by the same frozen hand. But the real mystery lies in what these similarities imply. For moons so far apart, their matching features are almost too perfect. Oberon, the outermost of Uranus' major moons, bears deep scars from eons of impacts, its surface a mosaic of bright icy patches and shadowed basins. Titania, closer to the planet, mirrors this pattern almost exactly. Same craters, same frost, even similar networks of valleys slicing through their terrains. This isn't just coincidence, it's a clue. Scientists suspect these moons might have formed from the same primordial disk of debris, a ring of ice and rock that once encircled Uranus in its infancy. Imagine a time when Oberon and Titania weren't separate worlds, but part of a single, chaotic nursery, their ingredients mixed together before gravity pulled them into their current orbits. Yet there's a twist. While their surfaces look like twins, their interiors tell different stories. Titania shows signs of past geological activity, hints of tectonic stretching, as if its crust once cracked under pressure. Oberon, by contrast, feels frozen in time, its features untouched by internal heat. So how did two moons born from the same materials end up on such divergent paths? Some researchers point to tidal forces. Uranus' lopsided gravity might have squeezed Titania just enough to warm its core, while Oberon, drifting farther out, escaped the same fate. Others wonder if a colossal impact reshaped Titania long after its birth, jump-starting processes that Oberon never experienced. But the most tantalizing theory ties them back to Uranus' greatest mystery, its extreme tilt. Planet spins on its side, likely knocked over by a cataclysmic collision billions of years ago. That same impact could have shattered a moon or even a passing dwarf planet, scattering debris that later coalesced into Oberon and Titania. If true, these frosted giants aren't just siblings, they're survivors of a cosmic demolition. Their matching surfaces a silent testament to the violence that shaped their parent planet. And if that's the case, what other shattered moon systems might be waiting out there? Astronomers have already spotted exoplanets with wild axial tilts, some even more extreme than Uranus. Could their moons also bear the scars of ancient collisions, their surfaces frozen into eerie symmetry. Oberon and Titania don't just challenge our understanding of moons, they whisper a warning. The universe doesn't always build worlds gently. Sometimes it forges them in fire and ice, leaving behind mirrors where we least expect them. Far beyond the orderly orbits of their planetary siblings, two moons drift like cosmic outcasts, Phoebe and Nereid, the dark wanderers. One circles Saturn, the other Neptune, yet both wear the same shadowed cloak of ancient craters and battered terrain, their surfaces etched with the scars of a nomadic existence. These aren't your typical moons. They move against the flow, tracing wild, looping paths that betray their true origins. They're interlopers, captured from the frozen depths of the solar system long ago. Phoebe, Saturn's enigmatic black sheep, spins backward in a defiant retrograde orbit, its surface so dark it absorbs nearly all sunlight, reflecting less than 6%, darker than fresh asphalt. Yet beneath that sooty exterior lies a startling secret. When NASA Cassini probe flew by, it spotted bright streaks slicing through the gloom, hints of water ice buried just beneath the surface. Even stranger, Phoebe's composition matches that of distant Kuiper belt objects, those icy relics from the solar system's birth. It's as if this moon was plucked from the outer darkness and hurled into Saturn's embrace. Nereid, Neptune's erratic companion, tells a similar tale. Its orbit is among the most eccentric of any moon, a lopsided, stretched ellipse that swings it wildly close to Neptune, then flings it far into the void. Like Phoebe, its surface is pocked with craters, its color a muted gray as if faded by eons of cosmic radiation. But here's the twist. Nereid's reflectivity changes as it rotates, suggesting patches of clean ice hidden beneath the grime, perhaps exposed by ancient impact. Together, these moons paint a portrait of resilience worlds shaped by violence, surviving on the fringes. What binds these dark twins across such vast distances? The answer may lie in the Kuiper belt, that shadowy realm beyond Neptune where countless icy bodies still drift. Phoebe and Nereid could be survivors of a chaotic era when the giant planets migrated outward, scattering debris and capturing wanderers like cosmic souvenirs. Their matching scars might be the fingerprints of that primordial turmoil, a time when the solar system was a demolition derby of colliding worlds. Yet the deepest mystery isn't where they came from, it's what they carried with them. Phoebe's surface is rich in organic molecules, the kind that could seed life under the right conditions. Nereid, though less studied, may harbor similar surprises. If these moons really are refugees from the outer solar system, they could be time capsules, preserving ingredients from a time before the planets took their current forms. That makes them more than just curiosities. They're celestial archaeologists holding clues to how the outer solar system, and perhaps others like it, came to be. So the next time you gaze at Saturn or Neptune, remember, their most fascinating moons might not be the brightest or the largest, but the dark ones, the wanderers, the outsiders, the ones that whisper secrets from the edge of everything we know. Among the many strange moons in our solar system, few are as downright peculiar as Hyperion and Proteus, two cosmic sponges drifting through the void. Saturn's Hyperion looks like it's been punched full of holes, its surface a chaotic honeycomb of deep, shadowy pits, some stretching over a mile wide. Neptune's Proteus, though slightly smoother, shares the same eerie texture, its craters appearing melted or warped, as if the moon itself is slowly dissolving. These aren't your typical impact scars. Their surfaces resemble pumice more than rock, porous and fragile, like celestial coral reefs frozen in time. What could create such bizarre, fragile worlds? Most moons are either solid rock or icy shells, their surfaces shaped by impacts or tectonic forces. But Hyperion and Proteus seem to defy the rules. Their densities are shockingly low. Hyperion is so light it might be half empty, a loose pile of rubble held together by feeble gravity. When NASA Cassini spacecraft flew by Hyperion, it detected something even stranger. The moon's craters are lined with dark material, possibly organic compounds, that absorb sunlight and deepen the shadows, giving it that unmistakable spongy look. Proteus, meanwhile, is the largest of Neptune's irregularly shaped moons, yet its surface is oddly dimpled, as if something prevented its craters from forming clean, sharp edges like those on other moons. Scientists have a few theories, and none of them are simple. One possibility: these moons might be the surviving fragments of a much larger body, shattered in some ancient collision. Imagine a massive moon, rich in ice and organic material, torn apart by a catastrophic impact. The debris, instead of coalescing into a smooth sphere, could have clumped together haphazardly, leaving gaps and voids that never fully compressed. It's like trying to build a snowball out of gravel. Some pieces stick, but the structure stays loose and full of holes. But there's another, even wilder idea. Hyperion and Proteus might be cosmic time capsules, preserving a type of primordial material that's nearly vanished elsewhere. In the early solar system, before planets and moons fully formed, there were likely countless porous, icy bodies drifting between the giants. Most were eventually crushed or melted, their structures erased by heat and pressure. But Hyperion and Proteus, they could be the last survivors of that forgotten era, frozen relics of a time when the solar system was still figuring out how to build worlds. And that raises a tantalizing question. If these spongy oddballs are remnants of a lost population, how many more might be hiding in the outer darkness? Astronomers have already spotted similarly pitted asteroids and comets, but finding another moon like Hyperion or Proteus would be a game-changer. It'd mean the solar system's history is written not just in the grand, sweeping arcs of planets, but in the fragile, crumbling pages of these strange, half-empty worlds. One thing's for sure: wherever these cosmic sponges came from, they're proof that the universe has a flair for the bizarre. And the deeper we look, the more we realize the strangest chapters of our solar system story might still be waiting to be read. Saturn's Iapetus is a cosmic paradox, a moon that shouldn't exist, at least not the way it looks. One hemisphere gleams like freshly fallen snow, reflecting sunlight with almost blinding brilliance. The other is darker than asphalt, absorbing light so completely it nearly vanishes against the blackness of space. This isn't some trick of shadow or angle. The divide is razor sharp, as if someone dipped half the moon in ink and left the other untouched. But here's where it gets stranger. Light years away, astronomers have theorized about an exomoon they've nicknamed Iapetus, a world orbiting a distant gas giant, yet bearing the same impossible duality, one side pristine white, the other drowned in darkness. How can two moons, separated by unfathomable distances, wear the same eerie mask? The answer might lie in a cosmic balancing act between heat and dust. On Iapetus, the leading theory goes like this. As the moon plows through its orbit, its dark side faces forward, collecting microscopic debris likely kicked up by impacts on Phoebe, another of Saturn's moons. This dust, darker than coffee grounds, piles up over eons, absorbing sunlight and warming the surface just enough to trigger a feedback loop. The warmer ice sublimates, retreating to the colder, brighter hemisphere, leaving the dark side even darker and the bright side even brighter. It's a self-reinforcing cycle, a celestial paint job applied by the laws of physics. But Iapetus, if it exists, poses a riddle. Without a nearby Phoebe-like moon to supply dust, what's painting its dark side? Some scientists speculate that thermal segregation might be universal. Any moon with a slow rotation and the right orbital tilt could develop this yin-yang split. On these worlds, sunlight would bake one hemisphere relentlessly, driving volatile ices to migrate toward the colder pole, while darker organic compounds clump together on the scorched side. It's not just about dust, it's about the universe's obsession with equilibrium, a drive to sort chaos into order, even across light years. The implications are profound. If this process is truly universal, then half-dark, half-light moons could be lurking everywhere, silent witnesses to the same forces shaping worlds across the cosmos. And that raises an even bigger question. What other patterns might be hiding in plain sight, waiting for us to notice the mirrors in the void? Iapetus and Japetus aren't just curiosities. They're proof that the universe loves to repeat itself, painting the same masterpiece on countless distant canvases. The only difference is how long it takes us to find them. Amalthea and Thebe might be small, but they punch far above their weight in cosmic intrigue. These jagged little moons, barely larger than city-sized asteroids, cling to Jupiter's inner orbits like flecks of rust on a giant's armor. Yet despite their modest size, they share a striking resemblance: irregular, potato-like shapes and surfaces stained a deep, burnt red, as if dipped in the same celestial dye. That color isn't just for show. Spectrometers reveal their hues come from sulfur, likely blasted off Eo's volcanic plains and scattered across space like cosmic graffiti. Over eons, these tiny worlds have been dusted and painted by the same infernal brush, their surfaces recording a shared history written in chemistry. But here's what really makes them fascinating. Amalthea and Thebe aren't just neighbors with matching paint jobs. They might be fragments of something much older. Their densities are absurdly low, suggesting they're less like solid rocks and more like piles of rubble loosely held together by gravity. Some scientists think they're the last survivors of a larger moon, one that strayed too close to Jupiter's crushing embrace and shattered under tidal forces. The debris, instead of dispersing, could have clumped back together into these odd little twins, their porous structures preserving echoes of that ancient catastrophe. Yet there's another possibility. What if their similarities aren't from destruction, but from construction? Jupiter's inner moon system is a traffic jam of orbits, where collisions and mergers were once routine. Amalthea and Thebe might have formed from the same ring of debris, a swirling disk of sulfur-rich dust and ice that once encircled the young planet. Over time, that material could have coalesced into these miniature worlds, their reddish patina a fingerprint of their birth environment. The implications stretch far beyond Jupiter. If tiny moons like these can mirror each other so precisely, what does that say about moon formation across the universe? Exoplanet systems often contain hot Jupiters, gas giants parked dangerously close to their stars. Could their inner moons also be littered with these sulfur-stained twins, forged in the same chaotic nurseries? Amalthea and Thebe might be small, but they're a reminder. Sometimes the universe's most profound patterns are hidden in the tiniest details. Saturn's moons Atlas and Pan look like they've been plucked straight from a vintage sci-fi movie. Their bizarre, saucer-like shapes defying everything we know about how moons should look. These tiny worlds, no larger than cities, are crowned with massive equatorial ridges, smooth and perfectly symmetrical, as if someone took a rolling pin to their middles while the rest of their surfaces remained untouched. From a distance, they could pass for UFOs frozen in orbit, their strange silhouettes hovering against the golden glow of Saturn's rings. But this isn't some celestial prank. Their uncanny resemblance hints at something far deeper, a hidden recipe for moon formation that might be playing out across the universe. What sculpted these ridges into such flawless symmetry? The answer likely lies in the very rings they call home. Both Atlas and Pan orbit within Saturn's intricate ring system, skimming just beyond the edges of the Rhea and Inca gaps. Scientists believe these moons act as shepherds, their gravity carving out those gaps while simultaneously gathering stray ring particles onto their own surfaces. Over millennia, as dust and ice rained down onto their equators, the material could have piled up into those striking ridges like snow collecting on a fence. It's a delicate balancing act. Too much gravity, and the moons would pull themselves into spheres. Too little, and the particles would drift away. But here, in Saturn's rings, the conditions were just right to craft these cosmic flying saucers. Yet the mystery doesn't end there. Why don't other ring moons like Daphne's or Pandora sport the same ridges? The difference might come down to timing and location. Atlas and Pan orbit in regions where ring material is fine and abundant, almost like powdery snow, allowing it to settle evenly along their equators. Moons closer to Saturn, where the rings are chunkier or more turbulent, might not accumulate material as smoothly. It's as if Saturn's rings are a cosmic assembly line, and only certain moons pass through the right stations to emerge with these iconic shapes. But here's the real question: could this process happen elsewhere? Astronomers have spotted similar ridges on small moons in other star systems, worlds orbiting gas giants with their own vast rings. If Saturn's recipe isn't unique, then flying saucer moons might be a universal phenomenon, a natural byproduct of moons forming in dense ring environments. Imagine countless star systems, each with their own fleet of tiny saucers, silently shaping and shaped by the rings they call home. Atlas and Pan aren't just oddities, they're proof that the universe has a flair for repetition. From the tiniest moons to the grandest galaxies, the same forces seem to paint the same patterns again and again. And if that's true, then the cosmos might be far more predictable and far more wondrous than we ever imagined. Saturn's F-ring is one of the most dynamic features in the solar system, a narrow, braided band of ice and dust that twists and kinks like a celestial ribbon caught in the wind. And right at its edge, locked in a delicate gravitational ballet, dance two tiny moons, Prometheus and Pandora. These so-called shepherd moons are the cosmic choreographers of Saturn's rings, their gravity sculpting the F-ring's sharp edges and intricate waves with the precision of master artists. But what's truly uncanny is how perfectly matched they are. Prometheus, the inner shepherd, and Pandora, the outer, are nearly identical in size, each about 80 miles across, and their orbits are so finely tuned that they seem to move in harmony, like partners in an endless celestial waltz. How does this symmetry persist across such vast distances? The answer lies in resonance, a gravitational phenomenon where two bodies exert rhythmic tugs on each other, their orbits syncing up like clockwork. Every 19 days, Prometheus laps Pandora, their gravitational embrace creating ripples in the F-ring that spiral outward like grooves in a cosmic vinyl record. But here's the twist: this dance isn't perfectly stable. Prometheus, drifting slightly closer to Saturn over time, occasionally plunges into the F-ring's inner edge, carving dark channels called gores into the ice. Pandora, meanwhile, tugs the outer edge outward, stretching the ring like taffy. Together, they're not just shepherds, they're sculptors, reshaping the ring with every pass. Yet the real mystery isn't how they shape the ring, but why they're so alike. Most shepherd moons in Saturn's system are mismatched, their sizes and orbits varying wildly. Prometheus and Pandora, though, seem cut from the same cosmic cloth. Some scientists speculate they might be fragments of a single, larger moon that shattered long ago, its debris coalescing into these mirror image guardians. Others suggest they formed side by side from the same ring material, their growth stunted by Saturn's tides before they could grow larger. Either way, their symmetry hints at a deeper pattern, one that might repeat around other ringed planets. And that raises a tantalizing question. If Prometheus and Pandora are products of a universal process, could other star systems host their own shepherd pairs? Astronomers have already spotted hints of Examoons orbiting gas giants with rings, though none yet with this precise duality. If they exist, it'd mean the universe has a favorite way of sculpting rings, not with solitary sentinels, but with partners bound by gravity and time. Prometheus and Pandora aren't just moons, they're proof that even in the chaos of space, harmony finds a way. Among Saturn's many orbital oddities, none are quite as mesmerizing as Janus and Epimetheus, two moons locked in a cosmic game of tag that defies ordinary celestial mechanics. Every 4 years, like clockwork, these sibling satellites perform an elegant swap, exchanging orbits with such precision, it's as if they're dancing to a silent gravitational melody. Picture it, Janus, the larger of the pair, drifts inward toward Saturn, while Epimetheus, its smaller counterpart, spirals outward. Then, without collision or chaos, they trade places seamlessly, their paths crossing like interstellar partners in a choreographed routine perfected over billions of years. What makes this orbital tango possible? The answer lies in their unique gravitational embrace. Janus and Epimetheus orbit Saturn at nearly the same distance, separated by a mere 30 miles, a hair's breadth in cosmic terms. Normally, such proximity would spell disaster, with one moon eventually ejecting the other or both colliding in a fiery crash. But these two have found equilibrium. As they approach each other, their mutual gravity creates a delicate push and pull. The inner moon accelerates, boosting itself into a higher orbit, while the outer one slows, dropping closer to Saturn. The exchange happens so smoothly that their combined gravity even sculpts the edges of Saturn's ring, leaving ripples as fingerprints of their synchronized motion. This phenomenon isn't just a curiosity, it's a masterclass in celestial mechanics. Scientists call it horseshoe orbit dynamics, a rare configuration where two bodies share nearly identical orbits but never quite meet, tracing paths that resemble a horseshoe when plotted over time. On Earth, we see hints of this with asteroids that co-orbit with our planet, but Janus and Epimetheus are the only known moons to pull off this swap with such precision. The secret lies in their mass ratio. Janus is roughly 4 times heavier than Epimetheus, creating just the right gravitational imbalance to keep their dance stable over eons. But the real question is, could this happen elsewhere? Exoplanet hunters have yet to spot a confirmed case of orbital swapping moons, but the math suggests it's possible. In young star systems where gas giants and their moons are still settling into stable arrangements, similar pairs might exist, moons born from the same ring of debris, their masses and orbits fine-tuned by chance into this rare harmony. Some researchers even speculate that early in our solar system's history, before moons found their permanent orbits, such swaps might have been common. If so, Janus and Epimetheus could be the last survivors of a forgotten era, a fleeting glimpse of the chaos and order that shaped every moon system. Their dance is more than a spectacle. It's a reminder that the universe loves patterns. From the spirals of galaxies to the orbits of moons, gravity weaves symmetry into the fabric of space, repeating its favorite melodies across the cosmos. And if Janus and Epimetheus are any indication, we've only just begun to hear the music. Saturn's moons Methane and Pallene are cosmic anomalies, tiny, egg-shaped worlds with surfaces so smooth they seem polished by some unseen hand. While most moons their size are pockmarked with craters, these two gleam like marbles fresh from the package, their icy exteriors almost untouched by the violent history that scars their neighbors. Methane, barely 2 miles across, looks like it's been dusted with powdered sugar, its surface unblemished except for faint ripples. Pallene, slightly larger, shares the same eerie smoothness, as if both moons were carved from flawless alabaster and placed carefully in orbit. So how do these fragile worlds stay so pristine? The leading theory points to Saturn's relentless influence. Both moons orbit within the E-ring, a faint band of ice particles spewed by Enceladus geysers. Over time, these microscopic snowflakes could have gently blanketed methane and pallene, filling in any scars like a cosmic skincare routine. But there's a catch. The E-ring's particles fall far too slowly to explain the moon's immaculate surfaces. Some researchers suggest electrostatic forces might be at play, sunlight charging the moon's surfaces, causing them to attract and trap floating ice grains like magnets. Others propose these moons are coated in ultra-fine, fluffy material, perhaps the remnants of ancient ring debris so light it settles like feathered dust. Yet the mystery deepens when you consider their orbits. Both moons skirt the edges of Saturn's gravitational danger zone, where tidal forces should stretch and fracture them. Instead, they've maintained their delicate shapes, almost as if their smooth surfaces act as armor, redistributing stress evenly to prevent cracks. It's a paradox. These moons exist where they shouldn't, looking how they shouldn't, and surviving how they shouldn't. The most tantalizing clue lies in their composition. Cassini's observations revealed that methane and pallene reflect light with unusual brightness, suggesting surfaces rich in fresh ice or even exotic organics. Some scientists speculate they might be porous snowballs, their interiors laced with empty spaces that absorb impacts without leaving scars. If true, they could be relics of a lost population of fluffy moons, worlds so fragile that only a handful survived Saturn's chaotic early history. But here's the real stunner. If methane and pallene are this delicate, why haven't they disintegrated already? The answer might rewrite our understanding of moon formation. Perhaps these smooth enigmas aren't ancient at all, but temporary sculptures, constantly reshaped by Saturn's rings and recoated by orbital debris. In that case, we're witnessing a fleeting moment in their lives, a blink in cosmic time before gravity eventually tears them apart. And that raises a haunting possibility. If such ephemeral moons exist around Saturn, how many others have come and gone unnoticed? Across the universe, countless tiny worlds might be flickering in and out of existence, their smooth surfaces a fleeting signature of a universe that never stops painting and erasing its masterpieces. Methane and pallene aren't just curiosities, they're whispers of a hidden chapter in the story of moons, one where fragility and beauty go hand in hand. Calypso and Callisto don't just orbit Saturn, they dance in its shadow, two tiny moons locked in an ancient gravitational waltz with their larger sibling, Tethys. These celestial companions are what astronomers call Trojan moons, occupying 2 of the 5 Lagrange points around Tethys' special zones where gravitational forces balance perfectly, like pockets of stillness in a swirling cosmic river. Calypso trails Tethys at the L5 point, while Callisto leads at L4, their positions so precise they never drift closer or farther apart. But what's truly uncanny is how perfectly matched they are. Both are roughly the same size, their surfaces coated in the same brilliant white ice, as if sculpted from the same block of frozen light. This symmetry isn't just a happy accident, it's a clue to their origins. Most Trojan moons in our solar system are lone wanderers, but Calypso and Callisto form a mirrored pair, their existence hinting at a delicate equilibrium that might be rarer than we thought. One theory suggests they're fragments of a single object, shattered by an impact long ago and captured by Tethys' gravity. Imagine a moon-sized snowball, struck by a rogue asteroid and bursting apart, its debris settling into these two stable pockets like marbles rolling into divots. Over time, Saturn's tides could have smoothed their surfaces into the gleaming twins we see today. Yet there's another possibility. These moons might be cosmic hitchhikers, captured independently but shaped by the same forces. Tethys' Lagrange points act like gravitational flypaper, trapping passing debris and holding it in place. If two similarly sized chunks of ice wandered too close, they could have been snagged and polished by the same stream of micrometeorites and E-ring particles, their surfaces sandblasted into matching frosted glass. The real mystery, though, isn't just how they formed, it's why we don't see more of them. Jupiter's massive gravity hosts a swarm of Trojan asteroids, yet none have settled into such perfect mirrored pairs. Even Saturn's other large moons lack Trojan companions as precisely matched as Calypso and Callisto. This raises a tantalizing question. Is their balance a fluke, or does Tethys hold some unique key to symmetry? Some researchers point to its unusually clean ice composition, which might have generated just the right tidal forces to sculpt and stabilize its shadows. Others wonder if the answer lies deeper, in the way Saturn's rings once interacted with its moons, seeding Lagrange points with twin fragments. Whatever the truth, Calypso and Callisto are more than just orbital curiosities, they're a test case for the universe's love of patterns. If moons can mirror each other across space, what other hidden symmetries might be waiting in the darkness? Every time we find a pair like this, it's a reminder that chaos and order aren't opposites, they're partners, weaving the same designs across the cosmos again and again. Helene and Polydeuces might not be Saturn's most famous moons, but their existence raises a question that's been haunting astronomers for decades. Is the universe playing favorites with symmetry? These two tiny worlds, each no larger than a city, share an orbit with Dione, Saturn's fourth largest moon, tracing paths so perfectly mirrored they could be celestial clockwork. Helene rides ahead of Dione at the L4 Lagrange point, while Polydeuces trails at L5, their positions locked in a gravitational embrace that defies randomness. It's as if Saturn's system has a blueprint for moon making, one that keeps spitting out pairs like cosmic assembly line products. What makes this duo so puzzling isn't just their shared orbit, it's their stark differences. Helene is a lumpy, cratered relic, its surface pocked with scars from eons of impacts. Polydeuces, by contrast, is smoother, almost pristine, as if it's been hiding from the chaos of space. How can two moons born from the same gravitational dance look so unilike? One theory points to their sizes. Helene is nearly twice as wide as Polydeuces, making it a bigger target for wandering debris. Another suggests their compositions might differ, with Polydeuces coated in finer, fresher ice from Saturn's E-ring, while Helene's darker patches hint at ancient organic material baked into its surface. Yet the real mystery lies in their stability. Lagrange points are cosmic parking spots, zones where gravity and orbital motion cancel each other out, creating pockets of equilibrium. But they're not always permanent. A passing comet or a nudge from another moon could destabilize these delicate balances, sending a Trojan moon spiraling away. That Helene and Polydeuces have endured for billions of years implies something extraordinary. Saturn's system might be finely tuned to preserve these pairings. Some researchers speculate that Dione's gravity acts like a shepherd, gently herding debris away from its Lagrange points, while others wonder if the moons themselves are actively reshaping their orbits, adjusting their paths like self-correcting satellites. The implications stretch far beyond Saturn. If Lagrange points naturally sculpt twin moons, then every gas giant with a large satellite, from Jupiter to distant exoplanets, could host its own hidden duplicates. Astronomers have already spotted Trojan asteroids sharing orbits with planets like Earth and Mars, but moons are rarer, their formation requiring a precise cocktail of gravity, timing, and material. Helene and Polydeuces might be a glimpse of a universal rule. Where there's a massive moon, there could be Shadow's smaller companions waiting to be found. But here's the twist, not all Lagrange points are created equal. Jupiter's massive moon Callisto has no known Trojans despite its size. Uranus' Titania orbits alone. This inconsistency suggests that while the universe loves patterns, it doesn't follow a script. Maybe Saturn's rings play a role, feeding material to its Lagrange points like a cosmic conveyor belt. Or perhaps Dione's own history, a cataclysm that shattered a predecessor moon, scattered just the right debris to seed these twins. Whatever the case, Helene and Polydeuces aren't just curiosities. They're proof that even in the chaos of space, gravity has a knack for creating mirrors. And if we keep looking, we might find them everywhere, silent partners to the giants, whispering secrets about how moons are born. Kivyuk and Igerak drift through the outer darkness like cosmic nomads, two tiny worlds clinging to Saturn's gravitational embrace from distances so vast they barely feel its pull. These aren't your typical moons, no smooth ice or crisp craters here. Instead, their surfaces are stained a deep, rusty red, as if dipped in ancient blood, their irregular shapes more akin to battered asteroids than the polished spheres we're used to seeing. Yet despite their rugged appearances, these distant siblings share an eerie kinship, their orbits tilted at nearly identical angles, their compositions matching so closely it's as if they were carved from the same celestial stone. What binds these far-flung wanderers together? The answer might lie in their origins. Most of Saturn's inner moons formed from the planet's rings or coalesced in its orbit, but Kivyuk and Igerak are outsiders, captured interlopers snatched from the frigid depths of the Kuiper belt. Their dark, organic, rich surfaces bear the hallmarks of that primordial realm where sunlight is feeble and chemistry runs slow. But here's the twist, their orbits aren't just tilted, they're nearly parallel, suggesting they didn't arrive randomly. Instead, they might be survivors of a shattered parent body, fragments of a larger object torn apart by Saturn's gravity billions of years ago. The evidence doesn't stop there. Spectroscopic analysis reveals both moons are coated in Tholons, the same complex organic gunk found on Pluto and other distant worlds. These molecules form when methane and nitrogen are bombarded by radiation, a process that would have taken eons in the Kuiper belt's icy quiet. Yet somehow, Kivyuk and Igerak ended up in the same place, wearing the same chemical fingerprints, as if fate itself guided them to Saturn's doorstep. But the real mystery isn't just where they came from, it's why they're so rare. Saturn's irregular moon family is a motley crew, with members ranging from dusky red to pale gray, their orbits crisscrossing at chaotic angles. Kivyuk and Igerak stand apart, their symmetry a glaring exception to the rule. Some researchers speculate they're the last members of a once larger group, their siblings long since ejected or pulverized by impact. Others wonder if their shared tilt hints at a gentler capture, perhaps a slow spiral into Saturn's grip during the solar system's turbulent youth, when gas giants were still migrating and scattering debris like cosmic billiard balls. There's a haunting beauty to their isolation. While most moons cluster close to their planets or dance in resonant orbits, Kivyuk and Igerak linger on the fringes, their red hues darkening with every passing eon. They're relics of a time before the planets settled into their current arrangements, before the asteroid belt was carved empty, before the Kuiper belt became a frozen graveyard. And if they truly are fragments of a lost progenitor, they raise a tantalizing question. How many other shattered families are drifting unseen among the giants, their stories written in orbits we've yet to trace. For now, these distant kin remain Enigma's whispering clues, not just about Saturn's history, but about the violent, nomadic childhood of every planet in our solar system. The universe doesn't always play favorites, but when it does, the patterns it leaves behind can haunt us for centuries. Scathai and Mundilfari sound like names plucked straight from an ancient Norse saga, and in a way they are. These two shadowy moons, one orbiting Saturn and the other a hypothetical Examoon light years away, carry the legacy of Viking myths into the cosmos. Scathai, named after the Norse goddess of winter and hunting, drifts through Saturn's outer reaches in a steep, lopsided orbit, its surface as dark as a moonless night. Mundilfari, though unconfirmed beyond our solar system, is theorized to share not just its mythological roots but eerily similar orbital quirks, a tilt and path so alike they could be celestial twins separated at birth. What's uncanny isn't just their shared namesake but the precision of their movements. Scathai's orbit is retrograde, meaning it circles Saturn backward compared to the planet's rotation, a trait typically reserved for captured asteroids or fragments of long-dead comets. Yet Mundilfari, if it exists, might mirror this same rebellious path, suggesting a cosmic rulebook we've only begun to decipher. Mythology fans might see irony here. In Norse tales, Scathai and Mundilfari were figures of defiance, one a giantess who walked her own path, the other a father punished for his hubris. That their names now grace moons with such untamed orbits feels like the universe nodding to the stories. But the real mystery lies deeper. Why would two moons separated by light years share such specific traits? One theory points to chaos literally. The late heavy bombardment, that era of solar system violence we touched on earlier, might have scattered debris into similar orbits around multiple gas giants. Like leaves caught in the same whirlwind, these fragments could have settled into matching paths, their inclinations locked in by the physics of capture. Another idea, their darkness holds a clue. Both Scathai and Mundilfari are thought to be coated in Tholons, those reddish-black organics we've seen on Charon and Hydra. This gunk forms best in the frigid outskirts of star systems, where radiation cooks simple ices into complex sludge. If certain orbits naturally collect this material, maybe it's no surprise that distant moons end up looking and moving alike. Yet the Norse connection lingers like a ghost. Ancient cultures often wove celestial patterns into their myths, attributing meaning to the wanderers they saw in the night sky. Could Scathai and Mundilfari's names be more than poetic coincidence? Some researchers speculate that early astronomers unknowingly preserved oral traditions about cosmic repetition, stories that modern science is only now verifying. It's a stretch but tantalizing. What if mythology passed down through generations carries faint echoes of truths about the universe's love for symmetry? For now, these moons remain enigmas, one confirmed, one hypothetical, both whispering questions about how deep the universe's patterns really go. Whether Mundilfari exists or not, Scathai stands as proof that even in the chaos of space, certain designs repeat. And if we ever find its mirror among the stars, it'll be a reminder. The cosmos doesn't just build worlds, it tells the same stories over and over in the language of gravity and ice. Alberix and Ariapetus aren't just moons, they're cosmic hitchhikers, wandering through Saturn's domain with the restless energy of celestial nomads. Unlike the orderly, near-circular orbits of most moons, these two trace wild, lopsided paths around the planet, swinging close before hurtling back into the distant dark. Their surfaces, stained a deep reddish-brown, betray their origins. These aren't native Saturnians. They're likely refugees from the Kuiper Belt, that icy graveyard beyond Neptune where dwarf planets and primordial rubble drift like ghosts of the solar system's birth. What's truly baffling isn't just their shared exile, it's how they ended up with nearly identical orbital quirks. Alberix and Ariapetus both tilt sharply, their paths angled like crooked smiles against Saturn's rings. Their eccentricities are so pronounced that at their farthest points, they nearly escape Saturn's grip entirely, only to be yanked back by gravity's invisible tether. This isn't random chaos. It's a signature, a fingerprint left by whatever cataclysm flung them inward billions of years ago. The leading theory, a gravitational ambush. During the solar system's youth, Neptune's migration outward sent shockwaves through the Kuiper belt, scattering debris like a cue ball breaking a rack. Some fragments, like Alberix and Ariapetus, might have been slingshotted toward the inner giants, where Saturn's gravity snatched them mid-flight. But here's the twist. Their similar compositions suggest they weren't just random strays, they could be fragments of the same parent body, shattered before capture. Imagine a Kuiper belt object the size of a city, shattered by a collision, its pieces drifting apart only to be captured by Saturn in tandem, like siblings reunited by chance. Yet the mystery deepens when you consider their surfaces. Both moons are coated in Tholons, those complex organic compounds that paint distant worlds in rusty hues. But Tholons need time and cold to form, a slow bake in the outer solar system's freezer. How do these moons retain their dark coats after migrating inward, where sunlight should have bleached them clean? One possibility is that their orbits, though eccentric, keep them far enough from Saturn to avoid tidal heating, preserving their primordial stains. Another is that they're still gathering fresh material, micrometeorites or ring debris, that replenishes their dark veneer over time. The implications stretch far beyond Saturn. If Alberix and Ariapetus are captured Kuiper belt objects, how many other moons in distant star systems might share their story? Exoplanet hunters have already spotted gas giants with extreme orbits, some so far from their stars they could have easily poached icy wanderers of their own. This raises a tantalizing possibility. Moon migration might be a universal phenomenon, with nomads like Alberix and Ariapetus serving as cosmic breadcrumbs, tracing the violent histories of planetary systems we've yet to explore. For now, these dark, wandering moons remain Enigma's testaments to the chaos of the early solar system and the delicate balance that lets some fragments survive their epic journeys. They're reminders that even in the quiet of space, nothing stays put forever. Gravity writes its own rules, and sometimes, against all odds, it leaves behind mirrors in the void. Cyanak and Tarkek drift through Saturn's outer reaches like silent sentinels from another time, their names echoing the myths of the Inuit people, a culture deeply attuned to the rhythms of ice and sky. These aren't the smooth, predictable moons of Saturn's inner rings. Cyanak, named after the Inuit goddess of the sea, and Tarkek, honoring the moon spirit, are rugged and irregular, their shapes more like crumpled paper than perfect spheres. Yet despite their rough exteriors, they share an uncanny kinship. Both trace distant, looping orbits tilted steeply against Saturn's equator, as if they'd rather gaze into the void than bow to the planet's pull. What binds these celestial outsiders together? The clues lie in their origins. Most of Saturn's inner moons formed from the planet's dazzling rings, but Cyanak and Tarkek are outliers, likely captured fragments from the solar system's violent youth. Their dark, reddish surfaces, rich in organic compounds, betray their birthplace, the Kuiper belt, that frozen frontier beyond Neptune where dwarf planets and icy relics drift like cosmic fossils. Yet here's the twist, their orbits aren't just random. Cyanak and Tarkek move in near resonance with one another, their gravitational dances subtly synchronized across millions of miles. It's as if Saturn's gravity didn't just capture them, it orchestrated their paths like a conductor guiding wayward musicians back into harmony. The Inuit names feel eerily fitting. Just as the myths speak of spirits guiding hunters across treacherous ice, these moons seem guided by invisible forces, their orbits preserving echoes of their shared past. Some scientists speculate they're remnants of a larger body shattered long ago, their fragments scattered but never fully separated. Others propose a gentler story. Perhaps they formed from the same swirling cloud of debris, their compositions matching not by chance but by birthright. Either way, their kinship defies the chaos of space, a testament to the universe's knack for weaving order from randomness. But the real mystery isn't just their connection, it's their defiance of time. Moons this small and distant should have been jostled into unstable orbits eons ago, yet Cyanak and Tarkek endure. Their resilience hints at hidden stabilizers, maybe the gentle nudge of Hyperion's gravity, or perhaps Saturn's own magnetic field, acting as an unseen hand to keep them in place. Whatever the reason, their survival raises a tantalizing question. If these Inuit-named wanderers can cling to their orbits for billions of years, how many other paired moons might be hiding in the darkness, their stories written in trajectories we've yet to trace? For now, Cyanak and Tarkek remain enigmas whispering not just of cosmic forces, but of the human instinct to find meaning in the stars. The Inuit saw spirits in the sky. Modern science reveals moons shaped by the same ancient collisions. Both perspectives, it seems, were right. The universe doesn't just build worlds, it tells stories, and sometimes, if we're lucky, it lets us read along. Ymir and Lodge sound like they've stepped straight out of an ancient saga, two frost giants cast into the heavens, forever circling Saturn in silent defiance. Named after figures from Norse mythology, Ymir, the primordial being whose body formed the world, and Lodge, the trickster tied to fire and chaos, these moons couldn't be more fittingly paired. Both trace distant, looping orbits that move backward against Saturn's rotation, a trait shared by only a handful of the planet's outer moons. But it's not just their rebellious paths that bind them. Their surfaces, dark as charcoal and stained with the same reddish hue, whisper of a shared origin, a story written in ice and shadow. What makes these giants stand out isn't just their names or their orbits, it's the eerie precision of their kinship. Ymir, the larger of the two, spans about 11 miles across, while Lodge is barely half that size. Yet spectrographic analysis reveals their surfaces are nearly identical, coated in Tholons and complex organics that paint them the color of dried blood. This isn't a coincidence. These compounds form when simple ices like methane and nitrogen are bombarded by radiation over billions of years, a process that requires cold, stillness, and time, three things the outer solar system has in abundance. The fact that both moons wear the same dark cloak suggests they were born or reborn in the same frozen nursery, perhaps as fragments of a larger body shattered long ago. But here's where the myth and reality collide. In Norse legends, Ymir and Lodge were adversaries, one a creator, the other a destroyer. Yet in Saturn's realm, they're locked in a gravitational dance that feels more like kinship than conflict. Their retrograde orbits hint at a violent past, likely as captured objects from the Kuiper belt, wrenched from their original paths and forced into Saturn's service. Some researchers speculate they might even be remnants of a single, larger moon, torn apart by tidal forces or a cataclysmic impact, their fragments scattered but never fully separated. If true, their shared chemistry isn't just similarity, it's memory, a relic of the body they once were. The real mystery, though, lies in their survival. Moons this small and distant should have been nudged into unstable orbits eons ago. ejected by the subtle tugs of Saturn's gravity or the influence of passing stars. Yet Ymir and Lodge endure, their paths seemingly immune to the chaos around them. One theory points to their resonance with other irregular moons, a delicate gravitational harmony that keeps them in check. Another suggests Saturn's extended magnetic field acts like an invisible fence, corralling these wanderers before they can stray too far. Whatever the reason, their persistence is a puzzle, one that challenges our understanding of how moons live and die in the outer solar system. And then there's the namesake irony. Lodge, tied to fire in myth, is now one of the coldest known objects in the solar system, its surface hovering just a few degrees above absolute zero. Ymir, the giant whose body formed the Earth in legend, is a tiny, frozen world with no chance of nurturing life. Yet in their own way, they're creators, not of worlds, but of questions. Every time we study them, they reveal another layer of the solar system's hidden history, another clue about the forces that shape the darkest corners of space. So the next time you picture Saturn's moons, don't just think of the dazzling rings or the icy giants like Titan and Enceladus. Remember the frost giants Ymir and Lodge drifting in the silence, their dark surfaces holding secrets we've only begun to unravel. They're more than just moons. They're reminders that even in the coldest reaches of the cosmos, the universe has a way of turning myth into reality. For centuries, we thought our solar system held the only blueprint for how moons could form, but the universe loves proving us wrong. The recent discovery of exomoons, those elusive worlds orbiting planets beyond our sun, has shattered that assumption in the most spectacular way. These distant cousins, separated from us by light years of emptiness, bear surface features so familiar they might as well be celestial doppelgangers. Take Kepler 1622b, an Examoon candidate with icy plains crisscrossed by fractures nearly identical to Europa's, or the volcanic Examoon Kepler 1705b, whose lava lakes mirror Eo's hellish landscape down to the sulfur-rich plumes. It's as if some cosmic architect handed out the same set of blueprints across the galaxy, whispering, "Build them like this." What makes these parallels so staggering isn't just the similarity, it's the improbability. Moons form in chaotic environments shaped by random collisions, gravitational tugs, and the quirks of their parent planets. For two worlds born around different stars in different corners of the cosmos to end up looking like twins. That shouldn't happen by chance, yet here we are staring at the evidence. One explanation points to the universality of physics. Given the same ingredients, a gas giant, a debris disk, and time, nature might follow the same recipe, sculpting moons with predictable features. Tidal forces crack ice shells the same way in any star system. Volcanic activity, fueled by gravitational friction, will always paint surfaces in sulfur and fire. It's not coincidence, it's inevitability, but there's a wilder possibility lurking in the data. Some exomoons, like the hypothetical Neo-Titan orbiting exoplanet WASP-12b, show signs of methane lakes and nitrogen atmospheres, a near-perfect echo of our own Titan. The kicker, their host planets are nothing like Saturn. This raises a radical question. Could moons develop these traits independently of their parent worlds? If so, it suggests that given the right conditions, a thick atmosphere, a stable orbit, moons might evolve toward certain patterns on their own, almost like cosmic convergent evolution. Life on Earth shows us how unrelated species develop similar traits when faced with similar challenges. Perhaps moons do the same. The implications ripple outward. If moon formation follows universal laws, then the ingredients for life, subsurface oceans, organic chemistry, stable climates, might be far more common than we dreamed. Imagine every gas giant in the habitable zone of its star could host an Enceladus-like moon, its hidden seas warmed by tidal forces. Every Titan analog might be brewing complex molecules in its methane drizzle. The search for life has focused on planets, but the real jackpot could be these mirrored moons, repeating the same promising patterns across the galaxy. Yet for all the excitement, mysteries remain. Why do some exomoons resemble our solar system's oddballs, like Hyperion's sponge-like surface or Iapetus's two-toned face? Are these outliers, or do they hint at even deeper, undiscovered rules? With every new Examoon discovery, the puzzle grows, and so does the tantalizing truth. The universe isn't just vast, it's repetitive, crafting the same wonders again and again, as if to remind us you're not special, but you're not alone either. And that might be the most profound revelation of all. When confronted with moons that look like carbon copies across the void, scientists face a cosmic whodunit. How can worlds separated by unimaginable distances wear the same scars, the same colors, even the same weather patterns? The leading suspect, tidal forces, those relentless gravitational tugs that twist and flex moons like putty. Take Europa and Enceladus. Their cracked, icy surfaces are textbook examples of tidal heating, where the push and pull of their massive parent planets stretches their cores, generating enough friction to melt ice and fracture crusts in eerily similar ways. But here's the catch: this doesn't explain why moons around different stars, like Jupiter's Io and the volcanic Exomoon Loki Patera, share identical lava lakes. If tidal forces alone were responsible, their host planets would need matching masses and orbits, a coincidence so unlikely it borders on absurd. That's where the theory of parallel evolution comes in. Imagine two chefs given the same ingredients and recipe. They'd likely produce similar dishes, even working in separate kitchens. Moons might follow the same logic. Given a gas giant, a debris disk, and enough time, certain features, subsurface oceans, volcanic plains, nitrogen atmospheres, could arise predictably, like cosmic inevitabilities. This would explain why Titan and Neptune's Triton both have methane cycles, or why so many icy moons sport those telltale, wispy fractures. The universe, it seems, has a limited palette when painting moons, returning to the same brushstrokes again and again. But some mirrors defy even this explanation. Enter the interstellar migration hypothesis, the idea that moons might not always stay loyal to their birth planets. Just as rogue planets wander the galaxy untethered to stars, moons could be snatched from one system and delivered to another. Picture this: a gas giant drifts too close to another star, its gravity plucking a moon like a ripe fruit and hurling it into interstellar space, where another star's planet eventually captures it. This could explain why Scathai and the hypothetical Mundilfari share such specific orbital quirks, or why Saturn's Phoebe looks more like a Kuiper belt object than a native moon. If true, these mirrored moons might not be products of their current environments at all, but refugees carrying the scars of their former homes. Yet the most tantalizing theory bridges all these ideas: universal resonance. Just as musical notes harmonize based on mathematical ratios, moons might fall into predictable patterns dictated by the fundamental laws of physics. Tidal forces, orbital distances, chemical compositions all could converge to create the same outcomes regardless of location. This wouldn't just apply to surface features, but to entire moon systems. The synchronized dance of Janus and Epimetheus, swapping orbits every 4 years, or the Trojan moons Calypso and Callisto, perfectly balanced in Lagrange points, might be cosmic inevitabilities, repeating wherever similar conditions arise. The implications rewrite astronomy's playbook. If moons form and evolve through universal rules, then the search for life, or even habitable worlds, shouldn't focus solely on planets. A distant solar system's Europa analog, cracked and ocean-rich, could be a better candidate than its Earth-like neighbor. And if interstellar migration is real, life's building blocks might hitchhike across the galaxy aboard nomadic moons, seeding chemistry far from their origins. Ultimately, these mirrored moons aren't just curiosities, they're keys to understanding the universe's deepest rhythms. Whether sculpted by tides, chance, or resonance, their existence hints at a cosmos far more orderly and far stranger than we ever imagined. And as we keep searching, one truth becomes clear: the universe doesn't just create worlds, it repeats them. From icy twins to volcanic mirrors, these 25 moons aren't just celestial oddities, they're clues to something far bigger. Their uncanny resemblances, scattered across star systems, suggest the universe operates like a master sculptor, returning to the same designs again and again. Think about it: Europa's fractures, Titan's methane lakes, Io's lava plains, each one feels like a stroke from the same cosmic brush, painted onto worlds separated by unimaginable distances. This isn't coincidence, it's a whisper of hidden laws, processes so fundamental they transcend the chaos of planetary formation. Yet for every answer these mirrored moons provide, they unleash a dozen new questions. Why do some patterns repeat while others vanish into the void? Take Saturn's flying saucer moons, Atlas and Pan. Their perfect ridges seem tailor-made for ring-skimming orbits. But why don't we see these shapes around Jupiter or Uranus? And what about the outliers, like Hyperion's spongy surface or Iapetus's two-toned face? Are they flukes, or do they hint at rules we haven't cracked yet? The more we study them, the clearer it becomes. These aren't just quirks of our solar system, they're pieces of a puzzle spanning the galaxy, and that's what makes Examoon so thrilling. Every new discovery, like the lava-strewn Kepler 1705b or the hypothetical methane-drenched Neo-Titan, pushes the boundaries of what we thought possible. If moons around distant stars wear the same scars as ours, it means the ingredients for life, for oceans, even for weather, might be universal. Imagine 1,000 Europas dotting the Milky Way, their hidden seas warmed by tidal forces, or a legion of Titans brewing complex molecules in endless twilight. The search for life has fixated on planets, but the real frontier could be these mirrored moons, silently orbiting gas giants in the habitable zones of alien suns. So where do we go from here? Upcoming missions like Europa Clipper and the James Webb Space Telescope are poised to peel back the layers of these mysteries, probing icy shells for plumes and scanning Exomoon atmospheres for hints of chemistry. But the biggest revelations might come from AI-driven surveys, sifting through mountains of telescope data to spot patterns human eyes would miss. One day, we might even send probes to these distant twins, tasting their geysers or mapping their cracks up close. Until then, these 25 moons stand as both riddle and revelation. They challenge us to rethink not just how moons form, but how the universe itself builds worlds, repeating its favorite designs like an artist obsessed with symmetry. And if history's any guide, the next mirror we find could rewrite the rules entirely. So keep looking up. The cosmos loves a good callback, and the next act might be stranger than we've ever dreamed. Drop your wildest theories in the comments. Could these moons be cosmic breadcrumbs, or is there something even weirder at play? And as always, stay curious. The universe is just getting started.